So some of the text segmentation systems out there, we're obviously speaking a lot about this one convenient method. There are several out there which might scale better. I've used Melli, for example, if you have a Java backend where the Java Melli also is Java-based, and so the models you can create are integrated right into your JVM. So now we're going into a little more syntactic level where we're doing this kind of parsing, and we're trying to label each. Now that we've segmented the strings, we want to give it a membership, some kind of, not necessarily semantic, but we'll start with syntactic, the idea of part of speech. And here there's lots of, turns out that there are actually quite a large number of them that help in any analysis that you do on the text, and not just nouns, not just verbs, but determiners, existential theirs. Having this level of granularity helps you a little more. And the part of speech by tagging would often look like this, where colorless green ideas get labeled with the word right beside it. However, you can do the phrasing afterwards so that automatic teller machine becomes the noun phrase, the proper noun. Some shallow parsing is where now we're not just going to the word and associating a single label, but now we're trying to chunk them into these regions of text. So it's a larger segment so that the temporary no-fly zone becomes the noun phrase and the participle phrase around is separated. There's a wonderful demo here, link to a demo that you can run. Same with this one. This is data that you can use to help you with the labeling. Unfortunately, there's a bit of an offset problem, but the idea is one of the, which is not so visible here, the idea is that the B of the NP is the beginning, the B of this verb phrase, the B, now this is the more interesting one. This is the start of it, the beginning. This one's the inside, inside, inside. And so this entire four words become the noun phrase. So this is non-IID. The label is dependent on what was before. This means that you have to look back to see where it began. So this is a cheat to convert a sequential learning problem into a simple non-sequential one where the label is based on this word. But sometimes you need to look behind and ahead. That was shallow. Then you can go deeper. Now you don't just want the lower level of the tree. You want the entire tree. Now we're getting into some much more granular kind of an analysis of the text, which there's, depending on the sophistication of your task, you may need. So when you're comparing two sentences, for example, you can do it at the syntactic tree level, and that might can give you a little extra signal. Here's information on how to parse it with NLTK, well, with this chart parser, and then you get this sentence. There are some challenges with, which I'll mention maybe momentarily, the idea of prepositional tagging, but the Stanford Parser is also very popular and powerful. Here's a link to it and the output that it'll produce. Dependency trees are an alternative to a syntactic tree structure that is a little more intuitive. They're equivalent in terms of expressibility and capturing the syntax, but you'll see a lot of dependency parsing, tree parsing in some of the analytics that we do with NLP. And strangely, just recently, even syntactic analysis has become worthy of a Wall Street Journal article where Parseface is one of the Google models that was based on neural networks, and it's published, so you can download it and you can see the incremental improvement. It's getting very small, but as I recall, it was just even slightly better than human performance. So that's maybe one of the even though it's small, it's still really interesting and expensive. Prepositional phrase attachment is one of the fun challenges of NLP. So this is one of the classic jokes of who shot the elephant and who's wearing the pajamas. This requires often a sense as you need background knowledge to be able to do this with the right linkage of who can wear pajamas. Now we're going into semantic analysis. The idea of semantics is the sense that there's and these are some of the topics we'll cover, is the idea that you're not only trying to capture the underlying math, it's kind of the production process, but what is inside the head, what is that sign expressing in the brain. If we're looking at this page ourselves, we're thinking about the entire page, and the sign could be this page. So it's moving a little bit of more abstraction. And one of the classic tasks here is named entity recognition. Not only do now you need to chunk, after you do some syntactic analysis like part of speech tagging, you then also need to find out that Mr. Smith is a person and that Sue Simothy is a location. And this often involves the creation of features on your token, such as simple as, does it have a capital letter? Is it a dictionary match? Is Markov Jordan? No. Then maybe there's some patterns. These patterns here, this word machine 223 can sometimes be compressed, where any letter is put into maps to the letter A and any number maps to 0. So that's a compression that can help with the process of finding patterns and signal in named entity recognition. In this case, I've dumbed it down. I've put these labels of tokens. So this will be one of the common transformations that you'll have on data once you've done all this work of even synsets and PDF processing. You put the part of speech tag. You put whether it has a capital, whether there's it starts with a character, whether there's 4 characters. There's a lot of features you can go. This can go to hundreds of thousands to be a sparse matrix. And here's that labeling again, the BIO. These labels try to change the sequential problem into a linear one, and you can then deconstruct it afterwards to find out where the. But there are some patterns that should never happen, such as an I should never be preceded by an O. So there aren't any here. So your statistical model needs to be at least capture that sequential signal. So here's the a little more detail on it. So not only do you then want the B, actually, so there's a typo there, sorry. That should be a B. Not only do you want this label, then you add a second label, and that's whether it's an organization or a product or a product or a product. So that's a 2-step process. This is one of another challenge that I have. But here, one thing that you can capture here is that sentences themselves can be divided and annotated by often by a space to know that there's now an end of sentence. Who's used conditional random fields before? Now, a slightly smaller subset of people. This is definitely the sort of baseline, sort of best practice approach to do this kind of work. And there's plenty of CRF models out there, but now you're beginning to get into much more granular and not necessarily integrated solutions. So CRFPP and Mallet are the ones I've used, but I haven't explored yet whether, do you know if NLTK has included a CRF yet?
I don't think it
does,
or if it does, it's not popular.
Anyway, so now it's definitely getting into an area where you would invest a lot more energy to figure out how to integrate the solution into your production system. But it is nice as you add more data, it starts to get more process. And this is a kind of a representation that you'll want to get. It's, first of all, the number of features. As you add more features, there's a separation, there's a boost if you add more features. And also, if you have a baseline, then you can say, well, if you have very little data, you're doing below the baseline, let's say a heuristic, like a dictionary lookup. Some more shallow semantic parsing that I've done for some of the tasks that I've shown you is semantic row labeling, product title shallow parsing, and relation extraction from text. So let's work through those. Semantic row labeling is now trying to get a sense of actors and agents and who is doing what to whom. There are some templates for many verbs, many predicates. In this case, the predicate is, and this is agent 0, agent is Swiss. So there's you have to know who is the subject and the object. And accept is another type of predicate. So here's the agent, he accepts anything of value. And this other are modifiers, the negation of what is being said, so that's an important modifier. And then you can add, often these are additional properties, those he was writing about. One of the nice tools on this, actually I think I only have it as a note, underneath this is a tool in Illinois that allows you to visualize this. So I didn't use that tool for my own projects, but I do use it for visualizing because it's wonderful help. So we just did this, right, Matt? This synset corpus extraction. So we'll press on. And this is on relation mention recognition, or any two concepts mentioned in the text related in some way, and well, often in a specific way, but even in any kind of direct way. And one way to go about this is, once you've annotated all your entities, you look at every permutation, every combination, and determine whether there's a relation. It helps especially if you can connect each of these entities to a knowledge base, so you not only have that they're a person, but exactly which person, but even if the link, even if this knowledge base is very granular, like just person, location, and organization, then you can still find out relationships of, let's say, works for or is headquartered at. To do this, you definitely need to get detailed about what each sentence structure is, at least to get an interesting performance. And textual graph is often a representation that allows you to make connections between multiple entity sentences, because you now need to connect the fact that this sentence is followed by this one, is followed by this one, and so that you can make this connection that in this case, there's a case study involving logistic regression. Now you can, for each of those cases, positive cases, a label of true or false. There's a lot of false relations because most things are not related to everything. You can do these text graph based. You can also do concept mention based and ontology based. So this feature vector is going to be continually expanded and made longer by having more information, more signals. We showed you some early ones of part of speech tagging and sort of those kind of simple ones. But you can now that you've reached into the ontology down here, you can begin to bring some of the properties down here up to the node and then do a pair. Notice that there's two of them. There's two entities where it's finding a relation. We can bring in information from the ontology that way. And each time we do a bit more of this, you'll get slightly improved performance. That's what I showed you with that learning curve. As you add more features, you start hopefully getting stronger performance. But it's often a lot of work to prove this, as the kind of work that Matt showed is we'll add a few features here, and there's a cost to that. Here are some examples of work that I've presented. Unfortunately, some of the work that I've done in industry, I couldn't show you direct examples, but this, what I often do is then I also reproduce some of the results using public data. In this case, is some KDD abstracts, and it showed the ability to find the relations directly using the methodology. Now, product offer parsing. And so in this case, the parsing is, I mentioned this idea of going into the, just almost like the named entity recognition, but it's the location. But we can do a little more with it. We can then do some clustering of the offer feed. So every time that Amazon and eBay gave us one of these offers, we can then begin to use that information to do some cluster analysis, which we'll get into momentarily. And for example, it would be helpful then to map this into whether which category it belongs to. And this is that now, once we've done this, we can begin to treat it as a standard classification problem that we're much more familiar with using any logistic regression or support vector machine or neural net that you would like. Again, you'll recognize this pattern of the tokenization and having these features, except that you can begin to add, well, I was being sort of abstract before, but here's examples of the number of brands that have the word video in it can help determine whether this video processor is a brand, which hopefully it gets wrong, or at least it's a false. One thing that, as you experiment with these solutions, that you'll find is that you, as someone said earlier yesterday, that it's by exploration that you discover some of the patterns that you need. When we did this, the actual overall performance was not super. It was 57.7 F1. It can still, it was actually still helpful, but we wanted more. What we noticed, especially at some categories, like in this case, it's consumer electronics, books, home and garden, and arts and entertainment. Especially books have a very low performance. What we did is we did a separate model just for books. We removed all the text for non-book data, and then we got 82 F1. So now we're much happier about this performance. So it's when you notice that you have you want to improve your performance from what you currently have, you can start to decompose your data into types that you find have affinities. One way we did it is simply by testing every model with every learning models only from certain categories and seeing how well they performed against the category. And of course, if you train on only books, then you do horribly on consumer electronics, so there's not transferability there. But we found that arts and entertainment also benefited from just itself. But actually, if you include books and arts and entertainment, now you do the best on this category combination. And sometimes you can even remove a category to here. So, wow, there's once you get into the analysis of text, you can often be achieving performance that's not human level, and so you need to be creative to discover these properties. One of my challenges, this was fortunately this work result in the KDD paper, was what is the automated way to discover these possibilities? I'd rather not have that job security of doing this grunt work. Now, what happened when we used this nice example of, by doing this work, we discovered these different categories, graphics card, directional antenna, sleeping bag, as being in our corpus as categories, and then we added them into our lexicon. Once we added them to our lexicon, we gave a nice signal to our model, and look at this, all of a sudden we started to get clicks on those terms because the model started to feel confident about those terms actually being categories. Sleeping bag is a little problematic of a word because bag is typically not much of a product, and nor is sleeping, but the combination turns out was it needed that hint. And once it got that hint in our lexicon, it found it and it started to trust it. We retrain the model every week, so once it found these terms in the dictionary, it started to make use of them on that day. And then it justified the cost of all this work. It's a wonderful thing to be able to do that. So this gave us tens of thousands of more dollars a week, and so all the work that we did with the data science was justified because there was a nice clear connection to the effort. There's a website out there that allows you to do this process, and there's a paper. I can also point you to the code. We wanted to go even further, not to just do the bottom, because notice that some of these offers for products are quite long, and include sort of maybe they're doing keyword stuffing, where they start to put fast shipping and then iPod, every other kind of term there, because they just want to, when you do a search on Amazon, they want you to find it because they've stuffed it with all these words. But we did find a pattern where there's the important bit, and then there's the unimportant bit, and so we could do a classifier there to begin to put a little more structure of a central part versus some other uses for this product. And now we could do, once we had that central component, we started to regain our semantics of what the product was. And so, for example, it's this part, and now we could put that part in a Lucene-based kind of database, for we were using Elasticsearch, and our ability to query this information grew dramatically. So who uses, let's say, Solr or Elasticsearch out there? So if you have unstructured data, then you can do some pre-processing before you put it into Elasticsearch, break up your text and find the index, the content, then load it into Elasticsearch, so then you can query each category, each column separately. Yeah, there it is. So here's the approach. We just repeatedly split the phrase into central and app. We did have some rules. So you'll notice heuristics, such as the word for, we noticed was really clear. And there are some obvious telltale ones, like free shipping. And then, again, this showed you the kind of art of the state. This is an example of the result of the JSON load payload that we put up into Elasticsearch. Notice the incredible, now we have this additional properties that we can query against. So we find that this is one of the application areas to create these databases of text, but then putting the structure in so you can start to do more interesting analysis. So that, for example, when someone is looking for a video card, now they can go directly to this, and just from the text we were able to read it. We didn't have to have some humans annotate it beforehand. So next I'm going to talk about some of these NLP frameworks, but unfortunately they're in I didn't have them in this presentation, so let's see what happens. If I can go back to the other one. Or it looks like it finally created the PowerPoint. Nice. Cool. I'll try running it again from PowerPoint because it's more predictable. So NLP on Spark, we're a little newer to this. We began to use Spark since about November, but more in production areas since May, June. But we wanted to do some analytics on it. I've done a little bit of extra work, as I mentioned, in a document that describes your ability to do it through an EMR. EMR is Amazon's Elastic MapReduce, but Microsoft's got its own solution. And I'm not sure if I asked this or yet. Spark, who's using Spark or use Spark? Okay, so this, if you follow this document, you'll be able to claim that you've used Spark. It should take you about an hour and a half to go through it, but it's canned in there. So, and what it does is, well, there's, I won't go then into the details. Those images there that you see are the ones that you sort of need to like internalize if you wanted to find out, become a little more up on what it's doing. The document goes this way. We set up S3, so we're using S3, which is the service that Amazon has for hosting files. So in there, we're going to put the PDF files, so it's going to be a bit of a repeat, so that it's sort of a simple, and maybe a problem that often we have. It's going to convert it into text, and it's going to do the part of speech tagging, and put it back into S3. Well, I show you how to set up the Amor cluster, how to connect to the Spark cluster, and then it's also IPython based, so it's the cluster itself, when it starts up, starts in Jupyter IPython server, so you can just start talking to it and do a bit of the work that Matt's done interactively. I also show some files there to do the processing completely. So I have examples of performing jobs, and then I have some solutions on how to monitor the server and how to issue commands once you've tired of doing it all by mouse button to go from a command line. The thing with a Spark cluster is that it's always sort of running. You have to start it and you have to terminate it. You can forget to leave it on like I did here. And then this is per day cost, but it's not a lot of money. So I started a small server with 3 nodes for this, for exercising, and I paid $8 for it. But as I show you later, I'll go through the document a little bit. I think we're doing okay on time. But the nice thing about this other service is called Lambda, which, again, there's a document that goes through it, and you can claim that you've done a reactive serverless solution, is that you send files through an API, and you put the code into the service. It does all this NLP analysis that we've been talking about, the PDF to text conversion and the part of speech tagging, and it only starts up enough workers' effort to do that work, and then it brings it all down on its own. So you don't have to worry about the configuration of the cluster and paying for anything that's starting, because the maximum amount of work that you can do in one job is 5 minutes. So whatever you do it's meant to be very kind of fast. And if I'm beginning to start running into that 5-minute process to do all this PDF conversion in a big file. But what you can do is you can then break up where one Lambda starts to talk to another, one does the PDF conversion, then the other one does the NLP analysis. But I needed to keep it simple for this work. So this document has we have to describe the Lambda function in some IPython code. What I show in Spark, the nice thing is what I did in the Spark world, I copied and pasted that and put it into there. It's just Python code. There's a couple of lines you have to change. You package it, you put it into kind of a configuration, a zip file that you can then put it into Amazon. And then you deploy. Basically, you have to say, like, how much are you willing to invest in this? You can say, no, if it goes longer than 10 seconds, then stop. And then running and monitoring. I do have a demo of it. And so the idea is that you can upload the PDF into here. It does this code and puts into a file. I'm calling it .nlp. And back into S3, and the nice thing is that when I did it this way, it cost me $0. Well, and that's because in part they have a gratis level of so many seconds. I can vouch that as you start to do more of it, it doesn't increment to thousands of dollars, but I'm pretty sure it doesn't. That's the intent. And now I don't have to worry that the server's still running out there or that it's in a weird configuration. It just runs. So I do have this demo uploader that unfortunately it's a live demo for me, but there are some challenges with me giving you access, because now once you have direct access to my S3 bucket, you can put gigabytes of files in there and start to use it for your own website hosting. So trust me that I have the code for you as well to create this little tool to demonstrate that you can upload a file to S3, which is sort of a fun little tool anyway, just to see what's inside the S3, and then not automatically, but within under 5 minutes, you'll get an NLP file or not. And it's all triggered. I didn't have to worry about the triggering. It was triggered just by the file appearing in S3. Then it knew that this little function should start and do work. There's a few other, for me, my interest is in NLP, in PDF files or text files for NLP solutions, but it can do other wonderful, well, kinds of reactive models. If it goes beyond the 5 minutes, then the Lambda now, the sort of a recommended approach is that you do a container service to do the much bigger effort. But I haven't done this. Stay tuned. Maybe in a year's time I'll have a demo of how to set one of these up as well. I'll go through these documents briefly, just to show you they're real. And here, goodness, that's very, how do I go full screen on this?
Just have one myself.
Okay, all right.
You seem to be zoomed in.
I am incredibly zoomed in.
Control minus. Oh, there you go. You got it. F11 worked.
Okay. Well, this just shows you my my little app. But well, I don't know how much benefit there is from me going through, except I'll highlight some of the areas. So there's when you start this Spark solution on EMR, you need a script that describes the contents of that service. And so you'll notice in here is basically using it to run IPython. Not only, well, we have a few additions, like for NLP, then there's where is it? There it is, text blob. I've added a few things. There's PDF miner, and it deploys Jupyter. Once you've done that, you copy it to S3, and you can go to the, you can create your cluster. You can do it by hand, as I'm showing you here, where you can turn on Spark, you can turn on or off some other solutions, like an entire Hadoop service with Hive, so that's sort of fun. They describe the number of workers and how you're going to monitor it. You upload that script up there, and here's the code. Well, you could also run, as I'm typically doing, issue the work to the command to set up the cluster from a command line. And in here you'll notice that I'm allowing the bid, because I'm using spot instances to pay less, to pay only, say, $0.10 per hour. And then you get a node name, this one, which you can now talk to, and it takes about 20 minutes before the cluster comes up. One of the other challenges of using these solutions, as opposed to Lambda, is you have to wait for the solution to be provisioned. You get the IP, and then to do the IPython work, as maybe oftentimes when you do IPython work, it's right on your laptop, on your own computer. You now need to talk to a server that's out there, so tunneling of an SSH tunnel is needed to have a connection to one of those servers. You tested, you connected to EMR, so now I'm talking to a server. You don't need to add typically you don't need to add any Python packages, because we've already done that in the bootstrapping work. And now when you connect to IPython, there it is. I'm going to offer that, trust me that this was a real live screenshot. And you upload and you do a new. And you may need to set up the security groups, but I've done it so that this is just so you can get a little more sophisticated. And now I'm going to slide down to where it sort of gets NLP-like. And this is just a simple, actually maybe I'll check in who's worked with Python, and now maybe it's a, so in NLP definitely, well, there's plenty of options, but in part because of NLTK and in part because of all the growth in data science with Python would be a good, this would be a good way for you to claim that you've written in Python, say maybe. And there's that, but finally, it looks familiar to what you just did, Matt, of the part of speech. I want to grow this to show demoware that shows you the addition of all those other features for each token. That's to come. I'd love to work with any of you to get that implemented, at least in a sort of a open source method. I'll let you peruse this file because I've started to get sophisticated in there and making it ever more general, but there's also some simple approaches to do it, and I add some work on how to monitor the Spark cluster. This is a document for the idea of the Lambda function, which includes certainly the code itself, but it's the exact same code that you just saw for doing the PDF processing. There's the interpreter of the PDF and the conversion, and then you package that into a Lambda function. It's all right here, and then you put it up, and then you configure your trigger, so you say process the file if it's a PDF file. There it is, suffix PDF. Well, it doesn't actually test that it's a PDF. I just test that it has the PDF suffix. Cool. Well, I can't say that I've used this yet in production myself, but it definitely looks appetizing. And so since I wanted to make this a big data, one of the parts of the big data should be maybe the VIG data, is the velocity. And this allows you, I could just now upload all of KDD's proceedings, 200 papers, and it would process them all independently, and within under 5 minutes I've done all papers. So, to return, now we are here. We have an hour left. I don't know that we have another coffee break yet. I'll do a stretch your legs break now before we move to the final hour of the actual tasks that we can now begin to do beyond all the pre-processing that we've done. So as I mentioned, we have just only covered the kind of analysis that gives us a sense of the details inside the sentences, the text. That's what language is. But now that we have it, we can apply it in ways that are more practical and the application that you need. We're going to jump, I'm not going to present a slide where around here I had a couple of slides where we do classification and clustering. So classification and clustering of entire documents or the contents of documents is one of those application areas. So you can get a sense, a summary of what the documents are about, or you can begin to label sports documents to news documents. Matt's going to present some work he's done on the clustering of the topics. It's the scaling topic clustering. So in there, now do we have the link to this one? It's that link at the... Mm-hmm. So I'm going to add it to scaling topic clustering with the, if you search for scaling topic clustering, I'm about to put the document link there. It is on the notes.
It's in the notes.
It is in the notes on slide number 144. At the notes of that slide is the presentation that Matt's about to give.
Great. So first thing I wanted to do, we're going to do a little more depth into, we talked about the budget PDFs and the abstract, and then we just talked about parsing sentences. So here I'm actually going to show you like some actual data that we've hosted up on S3 in a public manner, so that you can reuse this data and walk through it and kind of recreate what we do, and give an example of how you could get domain knowledge kind of opened up. And so what I want to do here is this is a little, I put the HTML in the slides and also in the GitHub code that was posted online, that has this little snippet that will go ahead and load and view the documents that are uploaded to S3. So you actually use this on any S3 bucket. You have to have cores enabled to make it work, but it's just a little HTML file. You double click on it, and boom, you can explore a S3 bucket. There's other tools too. If you there are tons of ones you can do. They're more familiar. This is just really lightweight, so anyone can kind of pop in and start using it. And here you'll see we have these PDFs. These are kind of PDFs from mostly from 2013 and back when we did this data collection. And I believe there's something around 60 gigabytes of PDFs in here. And I wanted to show you what one of these looks like. And then we're going to go ahead and do some analysis in an unsupervised way to find out what are the topics in here, what are some subjects that we might care about, and do it on a micro scale, and how you would grow that up to parse all the data. Okay, so I've downloaded one of these documents that we had up there, and you can see they vary quite a bit. This document has they tend to put these nice big pictures. If you also look in the upper left corner, this is 438 pages. Local governments spend about 6 months a year building these things. They're a very high cost and investment by governments to track how they spend our money and how they do it efficiently and where everything's going in the health of the government. And they like putting these pictures and make them, more accessible. But they have a lot of information in them, and they're kind of hard to actually read. I'm going to page pretty quickly through this real quick and just show you there's lots of content in here, and they have these sort of high-level subjects they'll talk about, and in no particular order compared between governments. So if you're used to reading these, you can figure out what the content is. But if you're not, if somebody lands in one of these and reads these for the first time, they're actually pretty inaccessible, and you don't know what the common phrases are. What's the topic that we care about? So what we're going to do here is we're going to take a few of these and actually let's go find some of those topics and have a machine tell us maybe what some of these subjects are, so we can get more informed decision making and more informed question answering. Okay, so to do this, we're going to do some topic clustering. So to get the data that we're viewing, there's a few unsupervised techniques that we can look at using, and I'm going to walk through one that we've used successfully at OpenGov. And we use this in a different setting, but also I've done demos and talks in various ways on this code for this subject as well. So, one of the things that is sort of a problem is when you're doing this topic analysis, it's sort of a classification problem, but you don't know the number of classes. You don't know what's in there and what you're trying to discover. So you're trying to identify a mapping of an ontology or social content task. You want to basically find what the different groups or classes are in this text. And there's sort of two common paths for doing unsupervised techniques. The first is really utility optimization, right? This is what traditional AI is. You make an agent, you give the agent some rules and some reward function, you let it go crazy and go let it explore, and it comes back with, hey, I found these things, or I can repeat the path to something interesting. But these can be quite difficult to understand and manage and run. They can be very feature sensitive. They can get stuck in different places. They have their uses, but traditionally they're a little more work to manage. So instead, we're going to talk about this clustering, which is really, really useful for doing a lot of the sort of group hierarchy organization for us, and not have us have to manage everything that's going on. All right, so there's tons of options for clustering. Matter of fact, clustering algorithms have been around for several decades. Almost from the invent of computers, clustering data was a very common goal. Matter of fact, early classification was thought of as clustering, and there was many early mathematical approaches to how you gather data together. Later, that became classification and more robust models. But they've made a comeback because they're very good at working on graph data, which we've seen more and more and more of in the past decade, or representing matrix space in a graph. And of these, there's several options, and they kind of I listed a few here. There's a dozen or more variants. And at the bottom here, there's sort of two big main flavors that have traditionally been around for clustering. There's bottom up and top down. And essentially, what the difference between these two things is, bottom up says, pretend nothing's connected, and then try to combine two things. then combine two more things, then combine two more things, and keep going until you either reach the point where you want to stop or do everything and then evaluate which one you think is the best choice. And then top down is the opposite. You pretend everything is one big group, and then you figure out how you split it up, and you figure out how you split that up. A lot of these problems are NP hard. They're really, really challenging. So the really efficient and good processes for doing this are oftentimes greedy. They make additional assumptions in order to get computation time back into polynomial space. So, for example, one that I've used successfully, and it's got a lot of really nice properties of clustering algorithms, is called hierarchical agglomerative clustering. The original definition of the clustering algorithm is still kind of slow. Clustering tends to be a slow process with big O of m times n squared. So your number of edges and nodes can have a pretty big impact. M and m are the edges and nodes. But instead, if you take the greedy version, which was also published by the original authors of this algorithm, you get down to a much more reasonable edge times number of vertices complexity. But this clustering algorithm does is it makes this nice little dendrogram of relationships. So you get this tree structure of all the combinations that it combined up in making different numbers of clusters. And then what it does is it evaluates each of those and tells you which one it thinks is best. And you don't need to know any starting state. You don't need to know anything about the data you're already clustering. All it relies on is having good edges. So if you've defined edges that represent the actual relationship between objects, you get very good clustering properties out of this. Additionally, I was mentioning before, this is an example of some of the data that we process at OpenGov, and it's, here if you have these different groups, there's k-means is like the thing. I think I implemented k-means about 8 times in school. Like every single class was like, there's this algorithm you should learn, k-means. One of the disadvantages of it, you need to know k, and it's a little naive. It's a great place to start, but there's some ways of calculating k and doing more complicated things. Instead, if we go to hierarchical clustering, we don't have to really even think about it. It kind of gives us a suggestion, and it says, hey, here's some groups where the green relationships here are strong and the orange are weak. These are different subjects that might be related. And this is the dendrogram you see here that actually runs. It'll build this sort of shape up for you, and each of those pairings is 2 nodes coming together and forming a cluster. And it produces a quality score, so it has a way it evaluates how it chooses the clustering, also gives it a score for how good the overall structure is. And typically it does very well. I've tried it on a few different data sets and different patterns, and it generally gives you good results, not perfect, but something that's definitely unsupervised trustable. And then when you get all done with this, you'll get something like this where you can visualize the cluster. So this is clustering data in the local government space that was collected from Wikipedia, and then we ran it through this same algorithm, and you get some of the subjects just come right out of the Wikipedia links. You just do a crawler, grab all the data, and then throw it in here, and just a bunch of sentences, and it came up with these clusters. And you get some sense here of like these are some subjects that you actually know how to interpret now. And then the thing with this is a little harder to scale this one, but a lot of the computation is actually done in the edge generation. So while the big O is a big component, generating a good, nice, rich feature set to generate the weights between 2 edges is actually typically your dominating feature until you get much larger. For example, right now, today, we can run this on a single machine with 200 million edges and around 2 million vertices. It takes a week to do all the edge generation and the clustering and everything together on one machine. It's kind of the end of life for that process, and that's where you want to start parallelizing the steps that are slow and identify which ones. But first it'll be your edge generation, and then your clustering later will be a bottleneck. And luckily, some of those solutions are coming out on Spark has a graph library that you can use that is starting to implement some of these algorithms, and there's a few others out there that are distributed computing for it. All right, so we're going to show some code now. This is a little bit of a meatier one. And what we're going to do is, this is also posted on the top of the slides for how to get to this code. And what we're going to do here is we're actually going to read in some of those budget PDFs and parse the whole PDF. And we're going to find what are some topics in that data that we found. How can we identify maybe some subject matter that's important to budgeting in governments? So here we're going to have just some helpers for reading the file and the progress. When you actually run this code, a few of them take 20 seconds to run the steps, so it gives you progress as it goes, so you know that it's not broken. And then we're going to download some of these sources. I've already pulled them in. As a matter of fact, they're checked into the repos, so you don't have to do the download. You can just go ahead and go read these text files. These are all files that were just converted with PDF to text. If you want to do a little bit better, you can use PDF Miner. It does, and if you have some of those files in the upload are raw images, and then I would suggest using Tesseract. And I can post some code for doing that later for how to do those conversions. We don't have it in this tutorial. All right, so we're going to go back. We're going back. You can recognize we have this that punked. Punked is just the style of tokenizer, and it's kind of fun to say. And so we're going to get the stop words again. We're going to get the tokenizer, and we're going to go basically set ourselves up so that we can parse through and get these sentences. Sorry. We're going to make this sentence structure so we can kind of track the original content and the tokens that we generate as we go along. So otherwise, you get a lot of these sort of index I on dictionary blah or whatnot, and it's a little hard to read. And we're going to tokenize some sentences here. And this will just basically go and stem and pull out all of the words that we find in these sentences. Now, before, we could also slap in some of the algorithms that we used in the prior code segment with the more advanced, like generate a parse tree and other relationships. But here, actually, we're just going to do something really naive. We're just going to count the occurrence of words and use that as the relationship. So the overlap of the number of words is what we're going to use to say, this sentence is like that sentence. What that means is you'll find sentences that use the same words, but maybe not the same meanings of those words. So there's a path where we can do better if we want to. OK, so we're going to go through this, and we're going to get these sentences. And basically, we're going to get the source and the text conversion of these sentences. There's a few things in here where we will do things like we'll do some filtering and whatnot. But here's the root of what we're going to do. We get these sentences, and we have a bag of words, effectively. So each sentence is being converted into a bag of words that we're going to compare. And this Jacquard similarity is a really great way to compare bags of words. It has some disadvantages if you have unbalanced data. So if you have very short sentences and very long sentences, Jacquard doesn't do so well. There's an alternative we use where instead of dividing by the union, you can divide by, you can do more complicated things by like taking the min of the largest set, so you can get scale in different ways to adjust for your data. But generally, Jacquard is a great place to start. And we're going to set this little threshold for 0.4 because what happens is if you don't do that, everything has a relationship and you get a dense graph. Dense graphs, by the way, don't cluster fast. It doesn't matter what you do. If you have a dense graph, your clustering is going to be slow. And so this gives us some sparsity. If it's below 0.4, it's probably just noise, and let's just drop it. Great. And so here's something. Here's the implementation. I've commented out to show that we don't want to do this, and this is where edge generation can be expensive. And this is, I'm going to show you, this is a trick that's really nice we'll use to solve this problem. But basically, we could go through each sentence, enumerate through that sentence, and then go through each sentence again and do an n-squared loop and do every sentence to every sentence, get the score, and then threshold it. This is exceedingly slow. As soon as I add another budget PDF, my time goes up exponentially, which means I really can't, no matter how much I distribute this work, I can't get exponentially more machines to process it. And this is a really common problem in like large text classification and search. So one of the kind of nice things you could do is you can use min hashing. There's a bunch of different terms that it's called by. Shingling, the hashing trick, a few other things that are variants of this. And there's a nice little library that actually does this for you and has a few parameters, and I've set it up here. But basically what this does is it will hash the contents of these documents, or in this case our sentences, and it will bucket them. So it'll do a bunch of hashes, and it'll put them in different buckets. And it just so happens to be that the property of the hash function it uses says that things that have high Jacquard similarity are likely to end up in the same bucket. So what ends up happening is it's a preprocessor to say these might have a high Jacquard similarity. And you can actually reduce your growth of computation from n squared to n log n. So now you can do n log n comparison between documents by losing a little bit of accuracy. And there's some great papers on this subject. As a matter of fact, one of the award winners from yesterday at the grand opening, Yuri Lekshevitz from Stanford, he has some great documentation that's free online about this. And matter of fact, that's where I first learned it. I was a student of his back several years ago. And it's a great practical implementation in production. We use this all the time. And so what we're going to do is we're going to run and basically create these, enumerate these sentences, threshold them. We're going to put that threshold so that we don't, spend a bunch of extra time on wasted stuff. This is kind of just boilerplate for how to achieve what we're doing. And then we print out every 1500 what our progress is. And we basically insert the index and the hash that we use on that sentence. Now we're going to go ahead and now we can iterate through and process these sentences. And instead, we're just going to, each time we get these in a bucket, we're going to iterate through all the buckets that we have. And we're going to say, OK, now for each of the things in the same bucket, let's see how much they compare and make an edge for them. And then we just insert this in the network X. So we're going to get progress here where we iterate over and can basically set the Jacquard similar, the actual score. And then that will give us that Jacquard function up above. So we're going to take the bag of words. We're going to see what the overlap is and give that the score. So if you have two sentences are identical, you're going to get a score of 1. If you have a sentence that has one extra word, right, you're going to get n minus 1 over n. Right? So you're effectively going to get really nice score when you talk about the same exact things. This isn't perfect. Obviously, there could be noise, right? If you have two sentences mashed together, they're not going to match well to any sentence that has the partial match with it. But it gets you going in a good place. And then we're going to add an edge into network X, and now we have a sparse graph. So we'll actually, when we do this and we actually run, we've parsed these several budget PDFs, and we have 26,000 sentences. And when we parse that all up, we're going to get 36,000 edges. It's actually really important that you play with that threshold, see what a good number is. Generally, if you're on the order of 2 to 100 times as many edges as nodes, you're probably in a safe domain. If you have outside of that range, you probably need to adjust your thresholding or your edge generation. Or you messed up your bucketing and you're actually doing n squared and don't know it. That happens. And then here we have, we're going to go and run this clustering algorithm, that greedy agglomerative clustering. This is actually an implementation that we support at OpenGov, so it's on PyPy, and you can just download it as a glom cluster. And this thing will go ahead and run. When I first got to work in this problem, there was no open source variants for doing this clustering. Or rather, the only one that opened was the snap library, and it wasn't parameterizable. You couldn't pass any, and you couldn't configure it in any way, so it was kind of not usable for us. And so I've implemented a Python version here, and we've been using this for years. It's single thread, so it doesn't get distributed very well. So one of our tasks, and one of the great things if audience can help with at some point, is helping us parallelize these clustering algorithms. There's a few implementations, and I want to bring some of these more forward. And we run this, and so we ran, and this thing is going to find 782 clusters in 12 seconds. So we took 26,000 sentences, and in 12 seconds, we found that there are 782 clusters. Now, the quality of these clusters, we have no idea. Unsupervised. It just gave us 782. They could be all noise. They could be all really great subjects that we could look at. So what we're going to do is, well, first, let's go ahead and look at the clusters we have. So there's some things we can reuse with Jacquard to get Centroid and similarity scores for those clusters. So a centroid of a cluster, you can basically take all the things that got grouped together and find the one sentence that is closest to every other sentence. That kind of gives you this idea of what's the label of this cluster. It's a good heuristic for understanding what's inside of there. And then the second thing you have is the similarity of the clusters. How similar is everything to everything? So if we run that Jacquard for everything, end up in the same cluster in n squared, but remember the clusters group down, so you're actually really still in the n log n space, unless you do something wrong. And then that will give us like what's the entropy of the cluster. So you might have a cluster that has a great central name, but everything got clustered together maybe it's really far away because it wasn't quite sure how to break it up. And now what we can do is we can run this through, and we'll build these clusters, and then we're going to go ahead and plot out the different the scores of this. So we're going to get this plot down here, which is going to show you, and unfortunately it doesn't have labels, I should add that in. But basically we're gonna try to identify some interesting clusters and what their similarity is. And we're going to do what the focus. We're going to look at clusters that have they're between length 5 and 50. So we don't want individual clusters of size 1. They're kind of uninteresting. And we don't want clusters that have tons and tons of references. Those may just be like single words or sentences that are really common that don't have any information content. What we're going to do is run and get these and see what in general all of these focus clusters that we've selected what do they look like on the similarity pattern, how similar are they to each other. And then we'll do the same thing, but instead we're going to go ahead and make sure that that we grab only clusters that come from multiple sources. So remember the original we kept where the source of the content came from? It's useful now because what we could have is one paper, one PDF, could have 1,000 references of the same sentence repeated. And here we didn't know where we weren't analyzing in the clustering the source of the content to figure out whether we should generate a cluster. So here we just say, let's just look at the ones that only have, only come from multiple sources. And this is a good way to sort of filter out some of the noise. So these things, I tried before without doing these things, but you end up seeing a lot of noise. So it's hard to see the nice content in there because we don't do smart things up above. We're really naive here. When we run this, we'll see the green is the focus clusters where they come from multiple sources, and the blue is the everything that was in that kind of range of 5 to 50 elements. And we actually see here is like these things that have really high similarity tend to be just redundant sentences that get repeated a lot. So you really, in this middle range is actually kind of your target point for finding interesting topics. And if you change your heuristics, if you make better functions that give better evaluation, then that interesting band will go up. So clusters will be more tightly coupled if you have better feature space. And so we're going to look at some of these and actually print out what the different cluster distribution is. So we're going to say how many clusters are there only have one thing in it? We need to know. This is the way you kind of analyzing unsupervised results and getting intuition about what your data looks like. So here we run the array. That's not useful. But here's the histogram of the size of the clusters. So you see, most of the clusters are pretty small. They're like 2 or 3 things. So they're kind of unique. The reason why we're seeing this is because we only parsed, I think, about 8 PDFs at the top. 26,000 sentences, just not enough content to get that nice score. So you remember you saw the scores before on Gabor's slides where, as you add more data and the logarithmic scale, you're going to get much better results. And in this case, you would see clusters of much larger size. So small clusters are generally bad. So we actually have only found a few clusters that have enough variety to be meaningful. But that was only parsing 8 files. So in 8 files, we found several topics that are actually probably useful. So what are the interesting clusters? We're going to go grab out the centroid. What's the central topic in these? You'll see here's the cleaning problem, right? We just blindly did PDF to text here, and we get a lot of noise in these sentences. But despite that, we still got some clusters that are actually interesting. So here this is like % of total department operating budget expenditures. Investment in the quality of Sausalito. You get the department revenues and expenses. You actually see that when you go through this, that one's pretty noisy. Accounts for use of fund balance is another grouping. So audited revenues. So you'll see that there's a lot of references to the fiscal year. There's a lot of references to fund balance and to expenses and revenues. So it's a little hard to see when you zoom in here, but if you're zoomed out, it's a little easier to see the clusters independently. And what we're basically going to do is, okay, well, that might have been a little hard. So what's some of we can find what are specific clusters out of it. Let's grab the first interesting cluster that was in our group. And in that one, we see this one is going to be the operating budgets for departments. So departments are actually managed by they have an operating budget, and they're managed by certain funds. So only certain funds can provide them money to do their job. And this is actually being captured here where it's talking about what % of the department operating budget is allowed to be spent by that fund. And if you actually look through this, that is what these sentences all refer to. So we actually found a topic that these finance experts talk about in these budget PDFs, like how much are we allocating for the police department this year from this fund? And you're actually getting a hint that there's this concept called multi-fund accounting. So you read through these topics, you're going to get more and more common terms and sentences that are said around the idea of multi-fund accounting. And I'll leave it to you. You can go ahead and run this and explore it. You will see noise, and if you go up to the top and fix things and make them better, you get less noise and more interesting clusters. And for the sake of time, I'm going to stop here on this, but there's like a way, we've done all unsupervised techniques, and the edge generation we saw was really slow there. We could parallelize really easily, and then the clustering part is the only part that is difficult to parallelize.
What else do you have, Matt?
After this, actually, that was my last. Yeah.
Okay. Okay, can we switch again?
Should I take questions?
Yeah, maybe. While I set up.
Do we have any maybe questions on it? That was kind of a run through of a lot of code and information. So also we'll be around afterwards for questions too. But if you have any questions right now while he's setting up the next segment. No?
Okay.
All right.
So we're nearing the end here. The last slide I have, I do have actually some other material. It is on the slideware, so help yourself to there. It's just that there's a lot of content here. Do want to finish a little earlier so that we could have time to make it to the event at the Grand Ballroom. But another popular topic that's related to what Matt just presented on the idea of understanding these clusters and the content are the idea of capturing these relatedness functions so that you can say things a little more explicitly. I want to see, I've given you a corpus in fairly unsupervised manner. That is, I haven't given you any labels. All of a sudden you say, I want to find more of this. Dress shoes, Oxford shoes, I've given you a hint, give me some more of those. And that would be, okay, let's find a cluster of those two, like what Matt did, but this is a different approach using the approach that was proposed through Word2Vec, which uses deep neural nets. However, since then, there's been similar work that suggests that you can use PPMI, matrix factorization, to achieve this exact same result. That's the impetus of doing this analysis. And it's pretty early on to do this kind of work, so the integration into actual production systems is nascent, but it's quite interesting for our exploratory exploratory steps, as I'll show. Or not like the other. So if you give these three terms, shoes, computer, and dress, can you tell me which one of those is not there? And that's similar to clustering. You start to explore the clusters and you see which ones belong in the same cluster. Now, this one's a little more interesting, the idea of an analogy, where what is, if a sneaker is to dress shoes, is what to high heels? Not that I happen to know what that is, but this would be one way to find out. There's a more kind of intuitive examples, but I'm focused on a domain that I used this at, let's say, at BigLink, where it was consumer products. The motivation for this kind of history is quite long for the use of lexical semantics, distributional co-occurrence lexical semantics. So if you see the word distributional semantics, it's the idea that words of a feather flock together. The idea that here in these three sentences, the word magazine and newspaper you see are sort of replaceable. They are very, very related because of the company of the words that they keep. Now let's look over all our text at sort of from the focal point of the word to see what company it keeps, and then build a representation of that space in a numerical fashion using vectors. The history is old, so the approaches date back to, and certainly some of the statements come back from even the 50s. But it's been recently that there's been enough data and interesting solutions to the problem of representing these words into vector spaces. So here's that word we were looking at earlier, newspaper. And this is a representation of those sentences that newspaper was found. One of them, you see the true and false. One sentence, you're just labeling which words were true for that word. Which were false. They all have different. And as you can imagine, now this representation, if you sort of squint your eyes, would be similar for newspaper and for magazine. But this is at a classification problem, true or false, in this very long vector of 671,000 words, because that's our lexicon. We're going to compress that 671,000 dimensions, simple dimensions, true and false, to a continuous one of about 200 dimensions, into a numeric one, which is about equivalent in ability to represent information, but more compact. And so what we want is that the word, now I've changed, this should say newspaper, but let's say chrome-plated instead. We're mapping that word to a vector of about 200 dimensions. We've done the squeezing in, let's say, singular value decomposition, but maybe a different way. And you get this vector, but it's a very dense vector. Before it was very sparse, now it's very dense. What does this allow us to do? Now, when we look at all the words in this space, remember it's a vector space with 200 dimensions, so you can just query this Euclidean space and easily look around the point. So this is one point in that space. It goes negative and positive, but typically between 0 and 1, negative and plus 1. So if you type France, now you can talk to the points around it, and you can look which is the nearest word to France by the company Keeps, and it looks like it's Spain, Belgium, Netherlands, Italy. So that's sweet that you can find all the European nations, or the ones that are near France, just by this process. So now you're beginning to get some semantics. Okay, this is a cluster, and I bet you these are nations. Now, what if you not generalize? Because notice that this is very European, and did I really mean to be have a European context? What then if you start to throw in other terms? So now that you have China in there, now Russia may begin to pull in, but it still hasn't done, by expressing it this way, still hasn't done the job of pulling in all the other countries. It could be your data. Now, this was done using Word2Vec. So we've stepped out of Python space. You can compile this. And the idea is that you first give the corpus into Word2Vec, and that gives you a model, this compressed representation. Now you can start to query it. So it's a two-step process. You first compress that data, and you find this vector space where this model, all it is each word has a number beside it, or a vector. You can do then, there's a couple of ways to query that data, but it's just numbers. So you train it, and you give it a sense. You have to give it a few dimensions, like the vector space, the number of dimensions, 200. Now there's some room to move there, but actually it doesn't make much difference in that order, to 100, 250, 300. And then the size of the window of the company Keeps, you can change that as well. And it's fortunately, although it is a parameter, it's not that brittle. You train, and now you have your model file. So now here's one of those rows in that file, the model file. There's the word watch. I keep switching on you, chrome-plated newspaper. This one's watch. And there's those dimensions, and here's a whole bunch of, that's what this file, that model is. Very simple and intuitive to understand. Of course, looking at 200 dimensions and putting that in your head is not so easy to understand. But you can start to do a little bit of visualization. Like, one of the dimension spaces like this, most of those numbers, as I mentioned, are between 0 and 1. Actually, they can go quite bigger, but that helps you to understand the properties of that space. And here are some just new and other examples. They're just so fun to explore, and also helpful. So for us at Wriggling at the time, we wanted to get the sense of brands that sort of were together. So the sport brands, the idea that Reebok now belongs to these other brands comes naturally from this concentration. Similar, the idea of Gucci, and let's say we wanted to substitute a product, and it was originally pointing to Gucci, and we sort of want to experiment with an alternative. Rather than sending them to Reebok, we could send someone who's interested in Gucci to, and also brands that I've never heard of, but I trust that they are sort of upscale. Maybe that says something about me as well, but to be explored and validated. So here's another one, the idea of colors. Colors are important in consumer products. So now you give the standard primary colors, and now you find others that are dominant in the space. So cool, there's the colors that are important in this space. One thing I did on this work is to look at different data sets. So this is Amazon, this is eBay, and then I could see when on different categories, on fashion offers, on home and garden, and jewelry, they have different representations of information. They all are present, but not always. So teal is not possibly a strong home and garden color there. So it's starting to show some of the challenges with this tool. It's not perfect. It's not a silver bullet. It's starting to add things that are not necessarily colors, like multicolor and colorful. And here's another bit of example. So for red, what you get, small, this is nice. What's related to small, extra large, small, large? This is like just by one step of training and no parameters. Okay, there are some parameters, but almost no parameters. Rule. And here's an analogy. Small is to S and large is to X. So X, I should have put not a question mark there. It is that small is to the letter S, but large is to the letter L. Great, so now I know some relationships that are analogical. There's relationships in the words. Here's another good one. When you add pink instead of the primary colors, you would expect to see something like this. Give me the pinky colors. And if there is a word of pinky. And sure enough, there they are. They are, well, fuchsia, purple, lavender, and magenta. But it's showing that there's only so much information. Maybe if we had a file that was 1,000 times bigger, then it would really, really zoom in on the important ones. But this is not big enough. We're starting to get noise. You can do clustering on this space. So just like, and this is using that k-means approach. So you have those vector space, and now you can just analyze the properties of that nicely numerical representation. And now you can find things. But in this case, you do, as Matt mentioned, you have to give it the number of clusters. In this case, I used 500. And you get some things like this. You get words that bundle like this. Alles, beer, Platz, and I assume that this has to do with drinking and beer and with a German theme. One of the other challenges when you deal with these is that there are sometimes inappropriate words, so forgive me if I included some in there, but no, I think I sanitized most of it. But there's like different forms of disease, different ages, decades. Well, and so what we do is we had a human annotate these. So this is where now the human can annotate, and we can begin to incorporate this information back into our lexicon. So there was an annotator that I mentioned who continually managed a repository, a lexicon. Now this benefited them to add more and put them together and to put these subclusters. Before we had very coarse clusters like product feature. Now we can get into things like style and 1970 styles. Which were those? Oh yeah, groovy and heartthrob in 70s. Kung fu fighting. I said, ooh. Here's some more of those clusters. For example, month was this one. So I highlighted some in orange, and that these were not found in part because, well, things like cancer are not that necessarily related to zodiac signs. So they might, the algorithm will not find that ambiguity, but a human could go, okay, it looks like zodiac signs are important. I can fill the rest. Once I've gotten the sense of what clusters are important in my data, the top 500 is sort of manageable. Now I can just fill them in and have a nice, beautiful representation of our semantics so that our system starts to look a little more intelligent and behave naturally. Here's another example where it starts to get all these batteries were one of the clusters and all these speakers just automatically. Like for Matt, some of those clusters are very busy, and so those are just noisy, and in a sense that's where the junk sort of just goes, where they're hard to pin. So most of the action starts in the middle. I was mentioning those relations. Here are some of the ones that you put. If you put China and Beijing, what is Russia? Then it goes to Moscow. What's Japan? It goes to Tokyo. So it finds, so one pointer in this 200 dimensional space for countries, and there's another point in the space for capital cities. And so now if you do this, they all maintain that same direction. Maybe a little bit different length and so on, but it's impressive. One of the highlights of this approach. Here are some others. What is Paris, France, Italy? What is sushi to Japan? In Germany, it's bratwurst. Fun to play with. I totally recommend it. The way it started is in the paper that suggested that king is to queen what man is to, and there it is, woman up there. But then, it isn't, you have to sort of pick the top answer, but there are alternatives which would be wrong. There is a set of questions out on the internet to train on or to at least measure on. Now there are breaks, so it's not going to always do what you hope to do because the data set is not big enough, say, so you have to discover what those boundaries are. Here's some more sample code to get started on this analysis. And we are done, except that here are some more tasks that you could explore. Here are some more other introductions to NLP. We're happy to help you get into this space. It's a wonderful time where the wave is beginning to grow. Thank you.
So I think we have a few minutes for questions, but before that, I was told to let you all know that lunch will be starting at 12:15 or pretty quickly. So there's a ticket on if you have your ticket for your lunch in the grand ballroom. That's the next event, and you can get in to get food. If you don't have a ticket, they recommend that you go over to the Yosemite room to get a streaming from the grand ballroom. But you'll have to. They won't have food provided, so you may want to go get something and then head over to Yosemite.
And I think we'll just reserve questions to if you come up to the front so that we can be a little more interactive. So please come on up for any questions.
Thank you.